Welcome to back, my students. Today's lectures. So we have discussed the points, applications of molecular orbital theory to heteronuclear diatomic molecules in the chapters of molecular orbital theory. In these lectures, we are going to discuss the points like applications of molecular orbital theory to heteronuclear diatomic molecules, molecular orbitals in heteronuclear diatomic molecules, unequal contributions of atomic orbitals towards molecular orbitals, and also we have see the reduced covalent energy. You know that the diatomic molecules, it means that two atoms of different elements, they can combine and to form the molecules, which is called as the diatomic molecules. These two molecules, they will have the difference, are named as heteronuclear diatomic molecules, and if these two atoms will have the same, which is called as the homonuclear diatomic molecules. But the atoms belonging to the different elements, they will have different electronegativity. It means that one of the atoms, they will have the more electronegative than other. Hence, the bonding electrons could be not uniformly distributed along these the two different molecules, two different atoms or the nuclei. The non-uniformity distribution of the electrons, the general partial ionic character in these molecules, they can develop. Now we have CR here, the molecular orbitals in heteronuclear diatomic molecules. We have CR here to form the molecular orbitals by linear combination of molecular orbital methods. For homonuclear diatomic molecules, we are see the combined atomic orbitals of the same type and to form each atom. But this was done required be since we expected that electrons in given molecular orbitals will be shared equally between the two identical nuclear centers or two identical atoms, and hence the electron can distribute between the two atoms equally. For example, the homonuclear diatomic molecules of the nitrogen, the electrons can distribute equally into two atoms. But however, sometimes we observe that in heteronuclear diatomic molecules, according to molecular orbitals theory, like the carbon monoxides do not have the same symmetry, because the carbons which is less electronegative than oxygens. Hence, electron density distribution between the two atoms, they will be different. And this fact, which is further supported by electron density counters for such molecules like lithium fluoride, hydrogen fluoride, and lithium hydride molecules. For example, these lithium fluoride molecules, we are C is here like a C, which is observed that this electron density counter, which is difference. It is also here the hydrogen fluoride molecules which is found to be such a type electron density counters, and other is lithium hydride molecules which is found such a type of electron density counters. And this is A and B, which is the electron density counters of the symmetric molecules. So for these electron counters, we can observe that the molecules will show their the electron distribution between the two atoms, and this further which can support using these electron density counters we can shows how the electrons get distributed. For example, first is a nitrogen electron density counters. This is a carbon monoxide electron density counter. It is a lithium fluoride molecules. It is hydrogen fluoride molecules, and it is a lithium hydride molecules. So we compare these all 5 diagrams. We observe that in homonuclear diatomic molecules, these electron density is distributed between the two atoms equally, right? Here in carbon monoxide, the oxygen is more electronegative than carbons, and therefore more of the electrons can pull towards the oxygen atoms, and hence such counters which is not the density which is not distributed equally, but it is distributed is a differently. Similarly, the lithium fluoride molecules also, these electron density which will be separate or distribute is a differently, and therefore this electron density distribute differently due to electronegativity difference between the two atoms, and therefore the treatment of heteronuclear molecules on the basis of molecular orbital theory, they revolves around the concept of electronegativity. In heteronuclear diatomic molecules, one of the atom is more electronegative than other. For example, in case of carbon monoxide, we know that oxygen is more electronegative than carbon. Oxygen is about 3.5 on pulling scale, and carbon is 2.6 on pulling scale of these electrons towards. But you know that the more electronegative atom of the oxygens, they pulls the electrons more towards itself due to electronegativity. Therefore, the bonding electrons, they will be more and stable nearer to the oxygen atom, right? Oxygen is more electronegative, therefore more of the electrons they get pulled toward itself. काय करतो, जास्त इलेक्ट्रोनेगेटिव्ह असल्यामुळं ऑक्सिजन आयटम स्वतःकडे जास्त इलेक्ट्रॉन्स ओढून घेतो, आणि ओढून घेतल्यामुळे काय होतं, त्याच्याकडे इलेक्ट्रॉनची संख्या जास्त होते आणि तो स्टेबल होतो, राईट, नियरर टू. In the other words, the electrons cloud will be distorted towards more to the electronegative oxygen atom in carbon monoxide. The difference in electronegativities of the combining atom in heteronuclear diatomic molecules leads to an equal contribution of atomic orbitals towards the molecular orbitals and reduce covalent energy. this difference of the electronegativities between the two atoms, they will lead to what happens? Unequal contribution of atomic orbitals, right? One of the atoms, they will have more contribute, other atoms, they will have small contributions of these electrons. And second points, they will reduce the covalent energy between the two atoms. So these 2 points which are very important with respect to these difference of the electronegativity having the heteronuclear diatomic molecules. First points we have see are here the unequal contributions of atomic orbitals towards molecular orbitals. We know that in homonuclear diatomic molecules, the atomic orbitals of combining atoms at the same energy, right? Homonuclear diatomic molecules having the similar atoms, therefore they will have the same energy, and hence they will combine the atomic orbitals and they contribute equally, right? The electrons is contributes equally like bonding and anti-bonding molecular orbitals. For examples, H2 molecules we have take one electrons of one atoms and one electrons of the other atoms, right? So one electrons they will contribute. So equal electrons will be contribute for these homonuclear diatomic molecules. One electron is a bonding and one electron is anti-bonding, like this. The linear combination of atomic orbitals, in such a case, we can write I R here. Psi b is equal to capital N B, means this normalized constant in bracket psi a plus psi b, and anti-bonding you can write like psi a is equal to capital N A in bracket psi anti-bonding minus psi bonding, where this Na and Nb which are normalizing constants for the bonding anti-bonding molecular orbitals respectively. In heteronuclear diatomic molecule, the atomic orbitals of the more electronegative elements which are more stable, right? In heteronuclear diatomic molecules which is more stable, they will have the more electronegative atoms, right? More electronegative atoms which are more stable than corresponding the atomic orbitals of the less electronegative element. And therefore, the heteronuclear diatomic molecules, for examples AB, the bilinear combination molecular orbitals, the bonding and anti-bonding molecular orbitals, we can write as like the homonuclear diatomic molecules. Hence, the psi bonding is equal to capital NB in bracket x of psi A plus y of psi B, bracket complete. Similarly, antibonding molecular orbitals of heteronuclear diatomic molecules like a psi A is equal to the capital Na in bracket y of psi A minus x of psi B, where this x and y, they are coefficient of the atomic orbitals. They will show their contribution towards molecular orbitals, and y is greater than x. Y they will have the more electronegative atoms and x with the less electronegative atom. Now we have see the atom capital B which is more electronegative, than capital A in AB molecules, then the contributions of the electrons more towards the molecular orbitals of psi B and less towards the antibonding molecular orbital psi A. On the contrary, the less electronegative atom capital A, right, means the capital B, which is more electronegative than capital A, than the atom capital A, which is more electronegative than capital A, capital B is more electronegative than capital A in AB molecules. That's time what happens? The bonding electrons, which is more in capital B, and antibonding electrons, which is more in capital A, contributes most towards antibonding molecular orbitals of psi A for those molecules, and less towards molecular orbitals of psi P. Now, second points which are very important to see are here: reduce covalent bond energy. We have seen in homonuclear diatomic molecules like A2, the covalent bond energy, which is maximum right here, the delta E of these molecules is which is maximum. This difference between the two atoms will be maximum. This H2 molecules we have take like this. So H are here, it is a H. So it is a bonding and it is a anti-bonding, sigma and sigma star. Sigma is a bonding molecular orbitals, sigma star is the anti-bonding molecular orbitals. We have Cr here, this energy difference between these molecular orbitals to these which are large in homonuclear diatomic molecules. Now compare with heteronuclear diatomic molecules are shown like these diagrams of molecular orbital energy diagram. Like in heteronuclear diatomic molecule, the combining atomic orbitals possesses the different energy, like this capital A, which is the less energy, more energy than capital B due to difference in electronegativity A and B, which has mismatched the energy of the combining atomic orbitals and leads to reduction of covalent bond energy. Note, the bond in such a situation is still covalent in natures, right? So energy difference between these atomic orbitals of this capital A and capital B, which is decrease because the energy gap also decrease and electronegativity difference also increase, right? Is capital A and capital B. So covalent bond energy is reduced, right? Covalent bond energy is reduced compared to homonuclear diatomic molecules like A2. But in this case, heteronuclear diatomic molecules, capital AB, with rather small electronegativity difference between these A and B. Now we have see other molecules where the electronegativity difference between these A molecules and B molecules is quite large. Hence, the covalent bond energy, they will further reduce or further decrease or almost negligible value as shown in these figures, because the electronegativity of this capital A and capital B, which is more, then it will be decrease, and hence the covalent bond energy is almost zero, right? Covalent bond almost zero means which is present ionic bond. In case of heteronuclear diatomic molecules like a AB with large electronegativity difference between this capital A and capital B minus, the bond is basically becomes ionic in nature in the molecules like capital A and capital B minus, right? So we can understand the molecules, they will have ionic bond or covalent bond in nature. The energy difference between is small, that times the molecules behaves as covalent bond, and its energy negativity difference between the two molecules is the very large, that times the molecule, they will show this ionic nature of this molecule. And from these three diagrams, we are conclude that the covalent bond energy successively decreases as the electronegativity difference between capital A and capital B will be increases, right? Means covalent bond energy which is decreased if the electronegativity between the two atoms will be increases. It may be wrongly believed that bonding in molecule AB successively becomes weaker and hence reduction of covalent bond energy. But however, which is observed that the loss of the covalent bond energy, which is compensated by increase in ionic bonding in molecules. Hence, we can remark that the total ionic and covalent bonding make very strong bond in heterodiatomic molecule in the intermediate situation, right? It is not difference is very large or not difference is very small, means is intermediate between these middle diagrams. These diagrams we observe the strong ionic bonds which is present molecules to show such a type of energy molecular orbital energy level diagrams.